Hello everyone. In this lecture, we will learn how to gather I/O statistics in relation to a process. So when I say I/O statistics, it could mean disk I/O operations or read or write on sockets or pipes or even your standard input, standard output. So all of these are broadly termed as I/O devices, right? So if you want to get the statistics on how many bytes have been read or written or what is the I/O traffic that's going on, you can just look up one file in /proc/pid, and it's quite intuitive and quite easy. You can just look up a file called /proc / any process ID. This time I'll use self. It'll give you information about cat command itself / a file called IO. There's one file which gives you all the high level metrics that you want to know related to the IO of this particular process. Let's try to understand what each of these values are, what each of these lines or the records represent. The first two records represent how many characters were read and how many characters were written. The char here is actually nothing but bytes. So this particular program, the cat command, has read so far 4092 bytes into memory. It performed reads up to 4092 bytes. It has not written any bytes at the moment of reading it. And how many read system calls were incurred is indicative of syscr. Syscr is indicative of how many read-oriented system calls were invoked. When I say read-oriented, it could mean read system call or p-read system call, AIO read system call, read-v system call, RECV system call. All of these are read variants of system calls. Similarly, you also have the write variant of system calls. How many write system calls were invoked? That is accounted by this number. Number of system call invocations is what these two numbers represent. And these read bytes and write bytes are specifically for disk IO. How many bytes were read from disk? How many bytes were written onto disk? That is your storage devices. So it looks like this cat command has never done any kind of disk IO. So it's all reported as 0. When you do frequent disk IO operations, like frequent write operations on disk, all the write operations are sent on a block queue, right? So if at all you have a pending write, right, on the queue, and a newer write would be superseding the pending write, the old writes on the queue could be cancelled out. So how many cancelled writes are shown are represented by this cancelled write byte. So all of these details you can see right here in /proc/pid/io. Now I will show you with another Python instance I'm running on my host. I've launched IPython this time, so it gives me easiness to repeat commands and all that. So the process ID of this is 18225. I just launched it and loaded OS module. That's it. So if you want to look up the IO information about this, you can do a cat /proc/18225/IO. You can see that the Python instance, or the Python shell in this case, has read up to so many bytes from all variations of IO streams, and it has written so many bytes. The number of read system calls invoked so far is 1334. Number of write system call or write family of system calls is 92. And this particular IPython instance has actually read up to so many bytes from disk and has written so many bytes on disk. And no writes have cancelled so far. Looks like all writes are unique. So if at all you open a file and you seek to the beginning of the file, write some data, again seek to the beginning, write some other data, seek to the beginning one more time, write some new data. The older data that you would have tried to write, if it's on the queue, they could be cancelled out. So that kind of cancelled accounting is shown here. This cancelled write bytes, you will see a larger number if you're trying to work on database engines. If you're working on database servers, if they're frequently updating the same record or same row on a table, they could be reported as cancelled write bytes by the underlying kernel, that is the Linux kernel here. So these are the details that you find. As a quick demonstration, I will also show you that if I try to open a file and read it, you can see this read bytes and write bytes, how they are updated. So I'll do one thing. I will cut this into two screens, two tabs. Right. So I could be running the Python shell in here. Oh, okay. I think I should do that after one moment, please. Let me go to the Python instance itself and now cut this screen across. So yeah, the Python instance running on the left-hand side. And here I'll try to monitor that. So I can just do a watch cat /proc/18225/IO. it's watching the file contents. As it changes, you'll see the updates in here. So in this Python prompt, as I start typing things, you can see all these are read and write to stand input, stand output, right? So you can see the accounting of that in read char, write char, sys cr, and sys cw, right? So this indicates the number of read and write system call invocations, how many bytes are being read and written. All these are accounted for simple IO operations, even on terminal. But you can notice that the read bytes and write bytes have not changed at all. So what I'll do right now is I will try to open some file, maybe a large file on disk. And the one that I can open is the Linux kernel. I think I can do that. So I'll just say f is equal to open of slash boot slash VM Linux. I think I have a VM Linux file. Let me just verify that. Nope, it's not there. They don't bundle this these days. The Linux kernel files are slightly big. I think it runs in megabytes. Let's see how big it is. 15 megabytes. Not so big, but quite large enough to report the number. So I'm just going to copy this particular path. I think the copy didn't work. Okay, let me try to use a middle click and see. Yeah, sort of. You can try and look up the read bytes value. It is 10. You can see that's here. It currently reports as 10690,560. But I'll try to open this file now and see if there's any change. Oh, permission denied. Okay. It tried to read some bytes, but it showed permission denied. I think I need permissions. I'll do one thing. I'll copy this as root user into my current directory, so it's easier. I just cause image.dat. So I have a file copied the Linux kernel as image.dat. There's a file, the home directory. I need to also make sure that the permissions are changed. The ownership, that is. And I can try opening this file now. So what I'll do instead, I'll try to open a file called image.dat, the current directory, open for read binary mode. It's a binary file, so I'm using RB. The moment I try to open the file, you don't see big changes in the read bytes. It is 108544400. You see some number there. But the moment I try to read the contents, I'll do a c is equal to f dot read. Oh, you won't see any data update. The reason is because I already copied that file once. It's a good thing to know. I copied the file once in the other terminal. When I copy the file contents are being read from disk and it's read into memory, right? And it's written back on another location on disk, let's assume. But the data that's read from disk into memory is maintained in the VFS page cache. Because it's maintained in the VFS page cache, this is not reported as read bytes. I will do one thing. I will try it on a VM. We will see that better. So in this virtual machine, I will launch. Okay, I'll try to launch IPython in one of the terminal like before. And I'll type import os.get.pid. I'll do one thing. I'll log in as root user because as normal user, I don't think I have permissions to access the kernel. So I'll have to copy that file, which will fill up the VFS page cache anyways. And the disk IO is not accounted for the process because the process does not initiate disk IO. It reads data from the data that's already hot in the VFS page cache. So I will log in as root user here. And maybe launch IPython. And the kernel in my machine, I think, is VM Linux -6.11.0-VBox. That's the kernel name. So I can verify that in the other terminal. (6.11.0-VBox). Sorry. It is quite sizable. I think it can see that it's roughly around 14.7 megabyte, I hope. Yeah, 15 MB, even here. So this is the file I'm going to read. I'm just reading ls command. ls command doesn't read the file contents. It just gets you the entry information and the inode information. Now let's go back to this process here, which is the Python process. And I'll create another screen, another tab window that is there. I'll also become root user in this case because I want to monitor this particular process. It's 1017. So here I'll just do a watch cat/proc/1017/IO. This will monitor the IO operations. Looks like the read bytes is actually 0. It's written something on disk. Yeah, IPython writes IPython history onto disk. I think that's why that's accounted as write bytes. Read bytes is still 0. Now here I'll try to initiate a read. I'll do a f is equal to open off /boot/vmlinuz-6.11.0-VBox. That's the file name. And try to open for read binary mode. No changes in read bytes because its entries are already on the VFS page cache. I'll try initiating a read. I'll do that by using c is equal to f.read. Now you can notice that the read bytes is accounted. 14 MB was being read from the file. The entire file I just read it into memory. So that's accounted as read bytes. If I close this file, open this file again and try reading it, you'll not see the read bytes increasing because very likely that file contents are on the VFS page cache. I can demonstrate that. So I'll close this file now. I'll just say del C. I'll use del C to get rid of the variable in Python. That means that data that's being read could be garbage collected by this moment, assuming no other references are there. And I can use f.close, close this file, del F, reopen this file, and call c is equal to f.read. Just notice the read bytes. It is currently showing as 14741504, whatever the number that you see there. And initiate a read. You see some write bytes accounted because IPython is writing all this into the history file, all these commands, but read bytes is not updated. What I'll do this time is I will close this file and del C as usual. I'll go to another terminal on this VM. And as root user, I can drop the VFS page cache, all the caches. So I'll do that by using sysctl vm.drop caches equals 3. That's a bit mask. It's like 1 1 in binary number. 1 1 is 3, right? So 1 bit to drop the VFS page cache, the page cache, inode cache, entry cache, all these are dropped. Another bit to drop the slab buffers. Try to drop all the caches for slab and the VFS page cache. Once I initiate that, now if I go back in here, I open this file one more time. And I try to do a read. You can see now the read bytes has increased. So the read bytes effectively tells you how much of disk IO was incurred by the process. If at all you open a file, it's not necessary that when you read data, it'll incur disk IO. It's very likely the file was read by other processes or it was read earlier by any process and the data is already there in the VFS page cache. That will be mapped to your process address space, right? With a private bit set. So it means you'll have a private copy, but it's all in memory operation. There's no disk IO involved. But this, if at all you drop the page caches, all the page caches are all flushed out or drained out. In such case, you can see that a read is initiating a disk read and that's accounted in read bytes. So if you really want to do, if you want to know how much of disk IO a task or a process is incurring, you just need to look up this read bytes, and how much of disk writes are happening. You can account it by looking up write bytes. So this is a quite useful feature to check whether a process is disk intensive, disk IO intensive. These are the only two fields that you need to worry about. And if at all you want to know overall IO operations, you can look up the read char and write char. How many system call invocations is read CR and write CR, syscr and syscw fields on this particular file. And the file is /proc/pid/IO. So this is all you need to know about getting the IO statistics of a given process. The last thing I should talk about is the IO latency. Whenever you try to read data from disk, there could be some disk latency. That is basically you try to initiate a command to a disk controller to read data. Some disk controllers will respond quick, but if you have some hard drives, they're very, very fast these days. But imagine a pen drive or an SD card, they can be quite slow. When you initiate a command to read, they'll take a long time to get the data into memory. So this is a disk IO latency. So if you want to know what is a disk IO latency incurred by a process, you can look up this particular entry, which is cut field number 42, there means delimiter space and /proc/ the process ID /stat. Remember, if you recall in the earlier lecture gathering CPU statistics, I talked about the stat file, which gives you a lot of process metrics. One field in this, that's a 40-second field, will tell you about the disk IO latency incurred by the process. If it shows 0, no latency at all because it's running on a VM, so you'll not see any latency. Let me try and attempt it on my real desktop. That's my Ubuntu laptop, where I have a pen drive connected, which is also mounted in a particular specific mount point. Let me try to copy a file onto that pen drive. Copy operations on pen drives are slow even today. Even with the days of USB 3, they are slower than a hard drive because there will be some latencies, right? So let's try to do that. I'm going to do that through Python. So for that, I'm going to use import shutil so I can monitor that process right here, right? So I can do that in here. So am I running on? Yeah, I think I am running on Ubuntu here. So I'll just do a shutil. This is a built-in module in Python which gives you some convenient wrappers to copy files and all that. So I'm going to use that. So I could run cp command, but by the time I monitor it, the cp command might actually terminate. But here the Python process will still be running even after the copy is completed. That's the reason I'm running through this shell. Okay. So here I'll just run shutil, and the file I want to copy is an Arch Linux ISO image, which I have in a particular location. So I'll just say maybe I can say ISO image equals in my home directory downloads folder. There's a file called Arch Linux ISO. So this is a file that I want to copy, but where do I want to copy it to? Well, this file is quite big. It's generally about 800 MB or so. It's hundreds of megabytes. So it's going to take some time to copy it. And the destination path I want to copy it to is, I'll just call this dest, is a mount point where I mounted this pen drive. As soon as I plugged in a pen drive, it got automatically mounted on my Ubuntu system under media /Chandra/ that's my username / I think, yeah, volume serial number. I have not set a volume label for this pen drive, so it uses serial number. So I'll just use this and I'll call this as image. I'll say Arch Linux.iso. I want to copy it as this file. And all I do is I can just use shutil.copy file of ISO image to the destination. So I'm just showing in Python, but you can do it in any language or you can run any command. So I'm just trying to show what happens when I'm trying to copy a file, because writing to the pen drive will be slow. We can account that in here. So in this place, what I'll do is rather than looking for read bytes, I'll create one more terminal below. It's better. So let's monitor this also, and I'll also create one more terminal. Oh, sorry. Yeah. So here I'll just try to monitor one more entry is I'll just do a watch cut minus field 42 minus delimiter backslash quote space backslash quote and under slash proc slash what is the process ID of this? I lost that information, I guess. Let me find out in here. It is 18225. 18225 slash stat. So slash proc PID stat. There, field number 42 is what I am trying to watch for. It shows 0 there. Let's let that be. So what I'll do now, we will try to run the shtutorial.copy file. You can see the read bytes and write bytes is now increasing. The latency is not recorded. The reason is simply because I think depends on the block device as such. So on a pen drive, I don't think latency reported. It shows 0. Not very useful. But if you try to use some external hard drives or any, not USB devices, mostly SATA hard drives or old generation parallel ATA hard drives and so on, this number records the latency. It depends on the storage device. Maybe the driver for this, it's not exposing any of these details. That's the reason it is showing 0. It's a proof. But otherwise, you'll see some number recorded indicating what is the IO latency. The file got copied immediately. So it looks like from the user space standpoint, the file is taken in, submitted, and that's it. The write operations are done in a very, very asynchronous manner in a dedicated K thread, right? So that's the reason this disk IO latency is not recorded for us process. It is done in a very asynchronous manner. So some other K thread is actually trying to copy this file within the kernel. We can even find that out if you just go and check it up in Linux. You'll see one of the K threads should be busy. Okay, I think the copy is completed, maybe because my pen drive could have been faster too. That could be a reason. Okay, there are too many things going on in here, so it's difficult to find out. Yeah, there's one task which seems to be, yeah. This is, oh, okay, this is a graphical driver. Sometimes you see a D state when the disk IO is still ongoing. So I don't see that here. So you will see that all the way below if that happens. So if I have a very slow pen drive, then very likely you would have noticed the latency. You would have noticed that, but you'll not see as latency, disk IO latency. But on some storage devices, the drivers will expose these numbers. Unfortunately, I could not demonstrate that in this particular video, but note down that field number 42. It might be quite useful, especially if you see disk latency is being reported by the driver. You will be able to notice that as field number 42, right? Yeah, because the IO operations are done asynchronously in a dedicated K thread, I think that is not reported or accounted to the process itself. Okay, so that could be a reason. All right then. So these are the different IO statistics that you can get from a process. Just 2 files. Technically, just 1 file that you need to care about. The other file didn't work, right, on a machine. So you can look up /proc/PID/IO. You can get to know about the overall IO reads and IO write operations. You can find out the system call overheads, how many system calls we invoke for read and write series of APIs. And you can also find out how many bytes of disk reads and disk writes have happened by looking up read bytes and write bytes entry in that file. That's about it. So this is what you should know about gathering IO statistics of a specific process. All right then. So with that note, I will end this video. I'll end this lecture here and we'll continue the next one. Thank you very much.